Okay, so in this lecture, we're going to continue with what we started with last lecture. One of the objectives, remember that, is to take an axiomatic approach to the natural number system. We begin by what do we mean by an axiomatic approach to a mathematical theory or to a mathematical structure. In such approach, we start with undefined terms, so some undefined terms, and we make a list of few axioms or postulates called, and then we can define new terms using the the undefined terms together with the axioms, and prove all the theorems that can be proven using this. All right. For example, you are familiar with the axiomatic approach to Euclidean geometry, where we have the axioms. We have first of all undefined terms like what is a point, a line, and so on. And then we have some axioms, and from there we define new terms and prove new theorems, and so on. Similarly, if you've taken a course in abstract algebra, most of the algebraic structures that are defined, such as groups or rings or fields, are in fact introduced axiomatically, all right, using an axiomatic approach. So, so that's what we're going to do for the natural number system. And in fact, this came to light in 1899. The Italian mathematician and logician, his name is Peano, introduced 5 axioms. They are now called, Peano's axioms. Okay, and they are very, very simple axioms, sort of. And from these, he derived all the properties. First of all, define the binary operations, which is addition, multiplication, on the natural numbers, and improved all the properties that you take as actually as given. For example, addition is commutative or associative, and so on. In fact, these are, we're going to see, there are theorems can be proving from these 5 axioms. So let me give the list of these axioms called Peano axioms. So to start with, remember that we need some undefined terms. So the undefined terms in this axiomatic approach to the natural number are the what do we mean by a natural number? I want to take this as sort of undefined term, and the term successor, which we're going to describe, okay, in terms that make it, make us to understand what it means. All right, but these are the 2 terms. Now, for Peano's axioms, we start with the first one. And Peano said that we're going to assume, suppose N is a set. We're going to call the set of natural numbers. All right. That satisfy. So these are actually just not okay. So we're going to suppose we do have a set. And we're going to see that this set is actually non-empty. So we're going to assume that suppose n is a set, its elements are, or we call this is the set of natural number that satisfy the following axioms. The fifth one, n contains an object denoted by the ordinary notation which we use for 1, but really this object could be denoted by any sim whatsoever. All right? So this means, or this axiom means, n, this set n is not empty. Second axiom, it says that for every natural number, for every element, for each n in n, there exists one and only one element in n called the successor of n and is denoted by n prime. Okay? Actually, from this axiom, which says that there exists one and only one element in n, that is we denote by this, which we call the successor. So from this axiom, we conclude that if we have m and n are in n, and they are equal to each other, then the successor of n should be the same as the successor of n. Because since they are the same, then we associate with each one of them one and only one successor. So it must be, the successor must be equal to each other. I will remark, the significance of these axioms, how they would actually produce all the natural numbers, and how also we can, just using these axioms, derive, we're not going to derive all the properties, but some of the properties to just convince you that actually this can be done. All right? Just a sample, short sample. The third axiom is the following. For any natural number, or any n in n, the n prime cannot equal to 1. All right? We need to explain what does this mean. This means that that 1 is not, all right, the successor of any element in n. All right? So 1 is not the successor of any element. Let me actually say n in n. All right. The fourth axiom, it says that if for some n m in n, we have the successor of n is equal to the successor of m, then n must equal m. So if we have two natural numbers or two elements from this set, they have the same successor, then actually these two elements are identical. The the fifth axiom is sometimes we call this is induction axiom. State the following: if k or let k be a set of natural numbers, what we call the elements of n, natural numbers, such that 1 or a 1 belongs to k. Second condition that this set k satisfies if k is an element in capital K, then the successor of k is in k. So if these conditions are satisfied, if there is a set which satisfies this, then this axiom says that k is equal to n. Alright, so these are the 5 axioms which we can actually derive all the properties of natural numbers, as well as from those we can build the system of integers, rational numbers, real numbers, complex numbers. Just these axioms is you can prove everything if you know about these different number systems using these axioms. All right, let me first of all reconsider the second axiom, which says that for every natural number there is a successor for the natural number. Well, from our experience, and because we don't know any better, it means that the n prime is equal n plus 1. Unfortunately, we cannot even make that assumption because we don't know what the plus means. All right? So the successor is, as I say, it is an undefined term. If you want to think for yourself, as actually it is n plus 1, that's fine. But in the proofs, we are not going to use this. All right? And all what we know so far, the existence of one element in n. And in fact, the second axiom, which will allow us to have more elements in n, all right? And we're going to see how this is actually done. And in the other axioms, of course, guarantee that the system that we are building actually is what we already kind of got familiar with, which is the natural numbers system. Now, remember the natural numbers or the counting numbers has been known to to humanity for many centuries, and billions of years, I don't know, at least thousands of years. and only this approach it is given in 1899. So way after people are familiar with all types of and properties of natural numbers. But we're going to try to avoid assuming that things that we know are going to affect the way we're going to actually approach the natural numbers. At least for this part, where we're going to kind of develop the natural numbers from these axioms. But later on, we're going to, of course, go back to what we got used to. All right? First of all, as a remark, the successor function, a successor, the term successor can be defined as a map. This is a set map. I have any kind of structure to it. S, if I put it S from N into itself. And by using this terminology, which we are familiar with from our experience in mathematics, a map or a function, another name for this. It's a rule by which S associate with every natural number, every element in here, one and only one element on the other end in here. That's the same. And that's exactly what the successor means. So in the language of maths, that's what it means. Now, the property which says that, which is axiom 3, remember this saying that if m prime is equal to n prime for some m and in n, then m is equal to n. If I translate this to the language of maths, means using S, then this saying that if S of m, because that's the way we denote the successor in here, so S of n, it really means the successor of n. Okay, so that's what S of n means. All right, so this one says that if S of m is equal to S of n, then m is equal to n. So this is equivalent to saying that this axiom 3 is equivalent to saying that S is an injective map. Or function, or we call it one-to-one, or one-to-one. Axiom 2 which says that 1 is not a successor of any n in n. This is equivalent, again, using the successor map or successor function, that S is not surjective. Or the older language is not onto. The function S is not onto. So in other words, we can actually use the modern terminology by thinking of the successor as a map. All right. Let me make a few remarks, okay, concerning these axioms. All right? And what's the significance of each one? Of course, the first axioms that tell us this set that we are assuming exists. It's not empty. It has something in it. So from the first axiom, we can conclude that only weight 10 contains one element. All right? The question is that going to be the only element? Well, we know not, of course. We know this is not true. And actually, the second axiom, so from axiom 1, we have at least using again 1 is a subset of n. All right. Now let's look at what the second axiom tells us. It tells us that axiom 2, it says that for every element, all right, in n, now we do have one, the successor of 1 is also in n. All right? And also we also know that the successor of any element in n, in this case 1, does not equal 1. So this implies by this axiom that 1 prime, of course, is another element in n and not equal. So this makes, so far, we have 1 and 1 prime. This one is contained in n. So we can use another symbol to denote the successor of 1. So let's use, okay, so we're going to let or denote by 1 prime by 2. So in other words, we're going to set that 1 prime is equal to 2. In fact, you can use any other symbol again, okay? But we don't want to get very wide, so we're going to use 2. So far, this is telling us that we have 1 and 2 is in n. Now, the question is, can we stop here? Can we say n is just 1 and 2? Then you might say, well, it means we need a successor for 2. Well, how about define the successor of 2 to be actually equal to 2? I cannot say 1, all right? So if I say this is equal to 2, then we have axiom 3. This will contradict axiom 3. So if we define, put it this way, if we define, all right, 2 prime, then by axiom 3, we have the successor of 1 is equal to 2, and also 2 is equal the successor of 2. This means because of these are successor of 2 different elements, okay, or 2 elements at least, or in terms of the successor map. This means S of 1 is equal to S of 2. And since S is injective, which means that 1 is equal to 2. And this is not true. This is a contradiction, right? Because we are saying that the 1 and 2 so far are different. Okay? All right, so it means we cannot actually stop it here. So we have to have another one. All right? With this, then we can say, all right, so we have so we started with 1, and then 1 prime, which we denoted by 2. In fact, I don't need to even denote this by 2, but then I can take the successor of 1, again, successor of 1, and take the successor of that, all right? And then we can keep taking successors like that. So axiom 3 actually allows us to keep going. Now to avoid, this messy notation, of course, we use, 1, and then the successor of 1 is 2, the successor of 2 is a 3, 4, and so on. Now, so far what we have is we created this set of natural numbers, and these are all contained in this set that we started with, being not empty within 1, and then we built it. We built all these numbers. The question is this it? Means, how would we know that? How we can say that n is in fact equal 1, 2, 3, and so on. Or to put it differently, is it possible to say we have this set n that we started with again, and then together with 2 other symbols, A and B, like this, which is larger in some sense than n, and define the successor of A to be B and the successor of B to be A. So if I take this as a new set, my n basically, okay, means I enlarge it. It turns out that this set actually satisfies the set n together with this A, B. This satisfies all axioms 1, 2, 3, and 4 by defining the successor of A to be B and the successor of B to be A. But we don't want this to happen, of course. Okay, now remember that we are assuming that the A and the B is none of those elements which we created so far. Okay, which is, it follows from these 4 axioms. Now the issue here is, or what make n, we cannot add to it anymore, okay, objects, is the 5th axiom, is the induction, okay? So the axiom 5 implies, all right, that n is what we know of. N consists of just successors of 1. If you want to do this, all right, you cannot have other symbols basically to it, such as an A and a B, which satisfy these two conditions. All right, so this is the one which we know of, basically. Because what it says that if you have a set of natural numbers, that is a set whose elements are coming from n, such that 1 is in K, if we call this set K, and if K is in K and the successor is in K, and that's what we have, now the way we build it in here, then this K is all of n, all right? And that's why we cannot add anything more. All right, our next objective is actually to define addition and multiplication on the set of natural numbers. But before we do this, let me put our next objective, and we need a lemma to actually justify the way we define addition as well as multiplication. Okay? So next objective to define addition and multiplication. Of natural numbers. All right, first dilemma. So let us state that if you have n is a natural number, and n does not equal 1, then there exists an element m in n such that this n is the successor of n. All right? So we're going to prove that this is the case. Okay? We're going to see that a lot of the things that we're going to be proving concerning addition, multiplication, and their properties, and so on, we're going to use heavily the induction actually axiom. Okay? And this is where we start with the first application of the induction axiom. So we're going to define a set K to be the following. This is n in n such that n equal 1, or n is equal the successor, all right, for some m in n. First, of course, in this case is a set whose element is a set of elements in n. That's actually the very first thing we're saying, n in n, okay, and satisfy that condition. First, we're going to see that one definitely belongs to k because it says n in n such that n equal 1. So it's already we are putting actually 1 is in there. The next thing I want to show that that actually k belongs to k. And we're going to assume such that k is not equal to 1. I know 1 is in there, so I want to take actually another. All right? Because this one is saying that, okay, so 1 or, all right, it's going to be a successor of some elements in n. So by definition of k, okay, by definition of k, we have k is going to equal the successor of m prime for some m in n. All right. Now remember in the induction axiom, we're going to show that if k is in k, then k, the successor of k is also in k. All right, so we have k is the successor. All right. And let's look at the successor of k. So this implies this one is going to be the successor of m prime, and we already know that this is in n because the successor of any natural number is a natural number. And it means that, again, by the definition of k, this belongs to k by definition of k. So by the induction axiom, we have k is equal to. It means that any natural number is going to be either 1 or actually a successor of some element, and this applies to all natural numbers. All right, now we need to proceed to define addition. Now we're going to see this now as crucial to see why addition is actually well defined for both. So we're going to define here addition. So for every pair of natural numbers, let's say m and n, and we assign one and only one natural number denoted by m plus n, right? And it is called the sum of m and n and is defined so that we call recursively, okay, by the following. First, n plus 1. Remember that we have for every pair, 1 is also a natural number, so we define this to be the successor of n. 2, we need to define m plus the successor of n. Define this is to be m plus n, the successor of n. Okay? And this is the first one. Both of these are defined for every n, m, in n. Alright, let's try to see if we could make sense out of this, and if this definition actually is well defined. So the first part of the definition, it tells us that we know that this n set of natural numbers has elements in it, and I'm defining to adding n to 1 to be actually just a successor, okay, of n. So we don't know if you're given an n, then there is a successor of n, and that one we define it to be the adding 1 to n. The second part, it says that if you take m and the successor of n, okay, then you could take the successor of the sum of the m plus n. Now let's see it here. So in other words, we are defining this, okay, this addition, basically, by the successor of something which we already know, okay? Now, let's look at what from the lemma, we know that every natural number basically is either equal to 1 or a successor of some other element, all right? So, so in here, if it is 1, you take the successor of this, and note that on the other hand, that natural number is going to be a successor, okay? Which is n prime, and then we define that to be the successor of m plus n. All right. Well, let's actually try to see how this does apply to adding some numbers. Okay. To make sure that we really see through this definition. All right. So let's look at an example. Of course, we have the 1 plus 1. All right, so our n for, let me put actually for n equal 1 in the definition. We say that 1 plus n is gonna be, what is it, 1 plus 1, okay? 1 plus 1. And we are saying this is equal the successor of 1. Right? And remember, we denoted the successor of 1 to be equal to 2. All right? Even I don't need to, but it's going to be the successor of 1. Okay? Let's look at if I want to add, for example, 1 and 2. Okay, so we already have the 2 as a successor of 1. So if I want to add 1 plus 2, so this is by the second part, this one is saying this is 1 plus the successor of 1, because 2 is a successor. All right? And part 2 saying that this is going to be 1 plus 1 successor. We already have 1 plus 1. All right? We already defined it. So this is 1 plus 1, which, again, if I use the simple 2 for it, it gives me 2 prime, and then, of course, this is we denote by 3. All right? And so on. So now let's assume we want to define it, actually add 2 and 3, because we already kind of have these in here. So let's say I want the 3 plus 2. Actually, 2 plus 3. Let me do 2 plus 3. So this is equal to 2 plus, we're going to recognize the 3 as a successor. And this is the successor of 2. Then we have this as 2 plus 2, successor of that. So in order to say what this is equal to, probably we need something before that. In other words, if I want to assume I don't have anything, and no clue what, how to add, I mean, just recursively do this one. So the next thing we wanted to do, maybe in a step in here, is to add 2 and 2. So 2 and 2, you're going to write this as 2 plus 1 successor of that 1. And then you write this as 2 plus 1, the successor of that. Then 2 plus 1, we already done this, or 1 plus 2. Actually, we might need to redo that one in a different way. So that's equal to 3. And the successor of that, and this is equal to 4. So in here you have the 2 plus 2. So and this becomes the successor of 4, and this is equal to 5. Of course, this is not a practical way to do addition, okay? But the idea here is we are not assuming anything, okay? We are just going from scratch, the basic, the very basic, all right? Let's look at how we define multiplication. And as you know, when you first learn multiplication in, grade school, you was introduced as a repeated addition. All right? So if you want to multiply 2 by 3, it means that you can add 3 to itself twice, or you add 2 to itself 3 times. So this is the way it was actually defined in grade school. And in fact, this is the way the axiomatic, all right, definition of multiplication is given. So one more time in here, the definition goes like this. For every pair of natural numbers M, N, we assign a natural number, actually one and only one and only one natural number denoted by m times n, like this. All right? And it's called the product of m and n in this order, and is defined by these two rules. Okay? Here. First one, we're going to take m multiplied by 1 is equal m for every m and n. Second, we want to define what we mean by m multiplied by a successor of n. And remember that every natural number either 1 or a successor of 1. So we have this one being a natural number. And we define this to be m multiplied by n plus actually m. And this is for every m and n. So these two rules, they give us a definition of a product of two natural numbers. Okay? And such a definition is recursive, because especially in here, we are defining this product in terms of, think of n being, the number before this n successor, right? That will be the old language. And and then we define it as addition. All right. Again, this makes sense because any natural number, either a 1 or a successor of 1. So and then that's what in the left-hand side, and this is the way it is defined on the right-hand side by things that already been established. All right. Once more, let's look at if I want to do the calculation of 2 times 2. Okay. So let's look at an example of multiplying 2 by itself. So we know that 2 times 1 is 2 from the first part. Okay, so let's do 2 multiplied by 2. So this is supposed to be 2 multiplied, this 2 is the successor of 1. So now we have a product of a number and a successor. And by definition, remember this one is equal to 2 times 1 plus this successor, this one without successor. Okay? So remember, this is the way we define m there. This is equal this plus that. Okay? So applying this. Now I know that 1 in here, this is equal to 2 from 1 plus 1. Now we already have 2 plus 1, we already established that, or I can go to my addition, and this is of course equal to, let me see here. So we have 2 plus 1, and this one is, the m is actually 2 in it. All right. I'm goofy? Okay. So this is the m, and this is the n prime. So this is a plus 2. And then we have, this is 2 plus 2. And then now we go to the way we did add the 2's. Okay, and we know this is equal 4. So we're going to end this. We don't want to go forever on this. All right. So I hope you could see that. Let's look at one more example. So I have another example in here. Let's look at 3 times 2. So this is a 3 multiplied. The 2 is 1. The successor of 1. And by definition, this is a 3 times 1 plus the 3. Okay, the m. And now this is a 3 plus a 3, and then go back to the addition, and then you know that what this is equal to, supposed to be 6, right? All right. Next thing we're going to show that the rules or the properties of addition and multiplication, some of them, actually we can derive from the axioms and the definition of addition and, of course, multiplication. So let's just start with the first theorem. And we're going to show in this that addition is associative. All right, so it states that for every m and p natural numbers, we have the m plus n plus p is equal m plus n plus p. In fact, so far from the definition of addition, we only can add 2 numbers. So if I have m plus n plus p without these parentheses, this is meaningless. Okay? We don't know how to add these. By putting parentheses, this means that we have to add the m and n and come up with, according to what we already know, that this is going to be a natural number, and then we can add this natural number to b. The associative property saying that you can get the same result if you add the n and the p first, okay, and then add the m to it in this order. All right. All right. Let's look at the proof of this. And again, we're going to see that we're going to be using the induction axiom. So we're going to let m, n be any natural numbers, and we're going to define a set of natural numbers okay, to be this. This is p and n such that m plus n. Now remember, these are given, the m and the n, and we define this set to be the set of all p's that satisfy sort of the associative property. So in a sense, again, make this one a little more transparent, we're going to sort of do induction on P, okay? So we are assuming the M and the N, and we are defining, this is just set of natural number satisfy this condition. And of course, what I'm going to show that this, in fact, is equal to N. So we're going to claim that K is equal to N. And we're going to do this, we're going to apply the induction axiom. Or again, in some sense, with the abuse of notation, we are doing induction on P, okay? And the statement that we're assuming we want to show that this the equality of these two sides. All right, so in order to do this, I need to show that 1 belongs to K. All right, so let's see here. So let's consider for P equal 1. What do we have? We need to look at M plus N plus 1 like this. And we don't need to remove the parentheses. Remember that by definition of addition, let me actually, because I need to have a series of these equalities, a rest of these equalities. Let me start at the top and have them all. Okay, so here we're gonna for P equal 1. So what we have M plus N plus 1. And I want to show that actually we can do the, the associative property for this, for these three numbers. All right? Now, by definition of addition, so this is an integer. Remember that we know this is a natural number. All right, plus 1. By the definition, this is M plus N, the successor. All right? So this is by definition of addition. Now, the M plus N, when we have this, also I can write this as M plus the successor of N. Again, this is by definition of addition. Same thing. All right. Now, this is equal to M plus, now the successor of N, I can write this is as N plus 1. Right? Successor of N is, this is again by definition of addition. Well, it means that this is the same as regrouping. So we have the M and the N together, and then we ended up with the N plus 1 together. So this means that 1 belongs to K. Now, the second thing we need is to assume that P is in K, which implies that M plus N plus P is equal M plus N plus P. Now, this is true for A. And then what we need to show that the successor of P is in K. Now, remember the familiar way we have, that which we will examine later on, actually, the principle of the first principle of induction is to show that P plus 1 is in K. That's what really this means, okay? But again, we're not making that even, assumption. All right? So, or we will use it because now we have we use the definition. All right? So let's consider then M plus N plus P prime. Okay, so I want to show that this is the same as rearranging take the M by itself and N and P prime actually satisfy the means it belongs to K, basically. All right? So we have this one is, we can write it as, okay, one way to write this is as M plus n like this, and plus p, and then we can put the successor outside. Again, this is by definition of addition. Then we can now use the induction hypothesis, or what we are assuming. Let me go in here. So I want to continue with this. So this is the left side in here. So far we know that this is equal to, okay, this m plus n plus p, and we have the successor. Now the quantity inside the parentheses in here, which is this, that's what that is. Then I can replace this by this. Okay, so this is equal m by itself and n plus p, okay, and successor outside. The reasoning for the equality between these is by assumption. Remember, because we assume p is in k, so it means it must satisfy this. All right, now let's continue. For writing what this is equal to. So this is equal to, so we have m plus something successor. So I can put the successor in this. All right, so this is definition of addition. Also, definition of addition, when you have two things added with a successor here, you can pass the successor inside the second thing. Like this. Again, this is definition of addition. Well, that's it. We're done. So we have shown that m plus n plus p prime is rearranged, and we got this. So this means, therefore, p prime does belong to k. So by induction, axiom, k is equal to n. Now what's k? K, it says that any natural numbers, when we add the b to it, it satisfies the associative. All right. All right. The next property that we want to show is addition is commutative. Okay. Addition is commutative. First, I'm going to show that addition of any natural number and 1 is commutative. Okay? And then we're going to use that lemma. We're going to state it as a lemma, and then we're going to show it's true for any natural number. Okay? So next, we need to show addition is commutative. All right, first element. For every n in n plus 1 is equal to 1 plus n. Means adding 1 to any natural number is commutative. Okay, and the proof of this, again, we're going to use induction axiom. So we're going to define K to consist of n in n such that n plus 1 equal 1 plus n. First, 1 does belong to k, since 1 plus 1 equal 1 plus 1. Now when I'm taking the n in here to be 1, all right, because it satisfies this condition, so it does belong to 1. So next we assume that actually k belongs to k. This implies that k plus 1 is going to be equal 1 plus k. I need to show that the successor of k is also in k. All right? Now, once I do this, then the induction axiom implies the statement is true, basically, for every natural number. Okay? So to show k prime is in k. Well, let's see, what does this mean? It means I want to look at k prime plus 1. And I want to see that I can commute these. Well, the k prime, as you know, it's going to equal to, this one is going to be actually k plus 1. Plus 1, like this. Okay? Let me actually do it in a different order, okay? So let me put in here actually 1 plus k prime. Let me go away with the k prime comes next. The way to define our addition. All right, so this is equal 1 plus k like this. Okay, and now I have 1 and k, then I can switch these. So let me write the reasoning here. So this is by definition of addition. All right. Now let's see from here where we go. So this is equal to k plus 1, like that. Okay. Again, this is by assumption, because I can switch k and 1 and k. Then this is equal to k prime plus 1. Again, this is by definition of, let me see it here. Actually, I want to do one more step before I can, because the k is in the wrong place. I have k plus 1. Now, the k plus 1, in fact, is equal, by definition again of addition, is the successor of k. Remember, k plus 1, that's the successor. And this is successor. All right? So this is by definition of addition. All right? Now, this is equal to, so we have a successor of something, okay? And we can write this as k prime, k plus 1. Okay, again, this is definite by definition of addition. Let's look at this, okay? Remember, in our definition, we said that we have 1 plus n is equal n prime, right? This is the definition of adding 1. All right? So in here, what I have the k like this. This is my n. And the successor of this is equal to 1 plus that. So I'm going backward. So, okay? So I'm going backward and writing it. And that's what it is. So we have 1 plus k prime is equal to k prime plus 1. I hope you understand, the dialectic arguments in here. Not very hard. They are just unique. We are really using the definition strictly, with nothing to add from a previous experience. All right. So with this, then we can conclude that k prime is in k, and by induction axiom, this implies k is equal to that. And what the set k is those natural numbers that actually do commute with 1. All right. Now we need to prove this commutativity for any two natural numbers. All right. So here is this second theorem. For every m n in n, the m plus n is equal n plus n. Okay, so addition is commutable. Again, the proof is use induction axiom. So we're gonna again for any. Let me see which one I want to take actually in here. For any natural number, so now also we can assume the m is given. Okay, for any natural number, we're going to define k. Now we know this is as a set of natural numbers, n in n, such that m plus n is equal to n plus n. Right. From the lemma, we have 1 is in k. All right? Because we already proved in here that m plus 1 is equal to 1 plus m for every m. We already established. So now I need to assume that, and I'm going to assume in here actually, let me see in here, k in k. And what does this mean? This means that m plus k is equal k plus m. All right? Where n is actually any natural. And I want to show that, need to show k prime is in k. Which means I want to show that the successor of k actually commutes with any m. So we're going to consider this, let me take m plus k prime. Again, by definition of addition, this is equal m plus k. and successor. This is by definition of addition. Well, let's see what this is equal to. I can, by induction or by the hypothesis, I can switch these. This is by assumption. Assumption there. Now let's get back to the definition of addition. So I'm going to bring in the successor to the m. So I can write this is equal k plus successor of m, again by definition of addition. Alright, I want to use that definition of addition again to replace m, successor of m, by m plus 1. Okay, so this is definition of addition again. Now I want to use the associative property. I could write this is k plus m plus 1. This is by associative property of addition, which we already proved, right? Then I'm gonna use that we have a natural number plus 1, so this is equal to successor of them. Okay, definition of addition. And now we need to go in here and we could write this one as k. Actually, one more time. We need the assumption one more time. All right. I want to switch the k and the m. So this is equal m plus k. Okay, plus 1. So this is by assumption. Now, m plus 1 plus k, this is the successor of that thing we are adding to 1. And so, okay, this is definition of addition. What was the step? Again, a definition of addition, this equals m. No, I want to switch the, no, I did not do this correctly here. Let me remove all this. No. Because I want to keep. Okay, so by the BC in here. Actually, sorry, I need to do one more. I want to use actually the lemma, by the lemma. Previous lemma, I can switch the 1 and the, as I said, this is very delicate, okay, argument. So I can do this. And now by associative property, by associative property of addition, I can rearrange these and have the k plus 1 plus m. And finally, k plus 1, I can write this is as k, the successor of k plus m. So this is by definition of addition. All right? And this is it. So m plus k prime is equal to k prime plus m. And therefore, the k prime, not the prime, means the successor is in k. and it makes the k equal to the m, and the elements in k are those integers that commute with every integer. Okay? So the commutative property actually does both. I want to give one more theorem that sort of do the addition and the multiplication. It's called distributive property. Property that connect both of these. Oh. This is the last theorem for today. Okay, that's there. It's called distributive. See, let's build this one. The property. And it reads like this again for every m and p natural numbers. We have the m multiplied by n plus p is equal m multiplied by n plus m multiplied by p. Again, as we done before, the proof is by using the induction axiom. So for any m, n in n, we define k to consist of those elements p in natural numbers such that the property basically holds. N plus p is equal m times n plus m multiplied by. First, we want to show that 1 does belong to k. 1 belongs to k. Okay, let's see why. It means that we have, this is equivalent to showing that 1 times n plus p is equal to putting, of course, a 1 for p in there. Sorry, I need to show that this is the wrong one. I want to look at m times n plus 1. Sorry, the p must be equal 1. Well, so let's look at what this is equal to. Well, this is equal to some multiplication, all right, of m and n plus 1, and I can write this is as m v times the successor. I replace n plus 1 by the successor. And now, by the definition of a product of m and the successor, remember this is m times n plus m. All right? And also I can use the definition of multiplication to say the m, I can put m times 1, right? And now we have this and this are the same. So I did kind of distribute the m inside the different. So therefore, yes, 1 belongs to k. The next thing we want to do is to show that if k is in k, then the successor of k is in k. All right. So assume that k is in k. Again, this implies that the we have m times n plus k. This is equal to m times n plus m times k. Or you could use p if you wanted to. Okay, to show k prime is in k. All right, to do this, we're going to consider again m times n plus k prime. Can I distribute the m with the k prime? All right, again, by definition of addition, we could write this as m times, these I can write as n plus k successor. Okay, definition of addition. All right. The next thing I want is to use the definition of multiplication. So we have m multiplied by successor. Okay, so this is equal m multiplied by successor, and this is equal m by this n plus k plus the m. Okay, so this is definition of multiplication. We put multiplication here. Now, we're going to use the hypothesis on this. Okay, you can write this one is m times n plus m times k. All of this I'm going to put between parentheses plus m. So this is by hypothesis, by assumption. It's not, we don't call them hypotheses, but we call it assumption. All right. Now we need to see what we can do. We need to use associative property. All right, and so we can write this is as mn plus, and I'm going to regroup m times k plus m. Okay, this is associative addition. Okay, so it's a property of addition. Now we need to use the in here again the multiplication. So this is m n plus, and this multiplication I can write as m plus k, the successor of k. Okay, so this is definition of multiplication. And then one more time we need to use the definition of multiplication, because we have something in here and then a successor. Okay, so that's equal to I'm going to continue from here. So this is equal to a quantity plus a, so let me see it here. The k prime is on, the successor is on k, and let me see it here. So we have m times k plus m. This is equal m plus the successor of k. And this is equal to m times n plus m times, sorry, this is we're going to use actually addition. So we're going to use the the definition of addition. So this is equal m plus n, k successor here. So definition of addition. All right. And now this is equal to oh, there's something did go wrong somewhere in here. Let me go back in here. All right, so we have M of this, and this is the distributive property for the assumption. M. Then in here we have used the associative property for this one in here actually is supposed to be mk by m. This is a product. I'm sorry. Here. This is definition of product. I'm supposed to have m times k. Okay. So m times k. And now we have, sorry, this one is incorrect here. Okay. Hope you see that this one is it's a product of mk, and now we have this, and then we have mk, and this is equal mn plus the successor supposes to be of mk. Okay, actually this one is mk by m. This is supposed to be k, the successor of k. All right, and now we do have, so this is the, actually this is it. What we have done in here, we showed that remember that we started with m, then we have n plus k prime. That's what we started with, and we have shown that's what we ended up with. This is m n plus m k prime, and which means that the k prime does belong to k, and hence k is equal to that. All right, so all the natural. All right, let me see it here. Probably I will actually stop right here. Next time I want to be talking about the ordering, how to define an ordering on the natural numbers, and prove a few things about it that we will really need to introduce what we call the will ordering principle. All right?